Okay, so today we are picking back up with 3B. And so to start off 3B, we've got, I'm on page 59 in your notebook. Excuse me. And so I want you to do this number 3 on your own. I want you to try it and send me your answer in a direct message. Let me share my screen with you real fast. And so we've got here, number 3 says a survey of 120 patrons at a restaurant gave the following preferences for their entrees and drinks. So we've got vegetarian versus non-vegetarian, i.e. meat or fish, wine versus no wine. There's 120 people total, and we've got the totals in other places. So I want you to finish filling in that table and then tell me how many people did not want wine with their vegetarian meal, and then how many people did not want wine with their meat and fish meal. Or excuse me, who did want wine with their meat and fish. Okay. So go ahead and finish filling out the table and then send me your answer to the 2 questions that are on there. So we can finish the table by doing 60 minus 20 would give us 40. So how many people wanted wine with their meat and fish? 40 people. The other one was vegetarian and no wine. So in order to get here, we've got to do 120 minus 60, giving 60, 60 minus 15, giving us 45. So then there was 45 people who did not want wine with their vegetarian meal. If we add them up, we can see we have 65 vegetarian meals, 55 meat and fish meals. Last check is always, do these 2 equal the last part, right? Is 65 plus 55 equal to 120? And yes, it is, right? All right, so let's go to the next page. Records for the Student Health Clinic show during 1 month, 120 students who visited for flu or anemia. 60 had flu only, 10 had flu and anemia. First of all, eat stuff with iron, people, right? You don't have to have red meat. Spinach has a ton of iron in it. Prevent the anemia. Like, flu's a whole other thing, but you can keep from being anemic. How many students only had anemia? So we're going to do the old Venn diagram. We got flu, we have anemia. So we know that 60 had flu only. So 60 having flu only is that half circle, the half moon on the right, where it's just flu, no anemia. And then 10 had flu and anemia, so that's where they overlap. And then we have this idea of 120 having flu or anemia. Flu or anemia is flu unioning with anemia. Okay, so what that means is if I give this region an amount X, I know if I add up those three regions, it has to equal 120 because the union represents all three of those regions together. So then combining like terms, 60 plus 10 gives me 70. Subtracting 70 from both sides, I end up with 50 just had anemia. So again, the important piece of information there was, what is the union? The union represents all of those regions together, right? And therefore we have to use that idea that it's all of it minus what we don't know. Okay. Sorry, I'm still taking roll really fast. Okay. So number 5, in a fraternity with 32 members. So first of all, as you're working through these, I want you to pick out your important information. So this 32 members is telling us that is our total population. Okay. So if I draw my rectangle, the reason I have a rectangle in number 5, but I didn't have a rectangle in number 4 is because it didn't tell me anything about all the students who went to the clinic. It had already focused on just for flu and anemia, so I didn't have this outside region. Here I've got 32 members in the fraternity. 18 take math, 5 take both math and physics. So that means we've got math and physics, and 5 of them taking both. 8 take neither math nor physics. So that's outside the math and physics bubble, but still within the fraternity. So they live out here. How many take physics but not mathematics? So we have used the 32, the 5, and the 8. So there's still that 18 taking math that we need to use. That 18 taking math represents my whole math circle. So because it represents the whole math circle and we've already used 5 in the intersect, we then need to subtract those out. So we're going to do 18 minus 5, which gives me 13 sole mathematics takers. So again, this is like what we did in number 4. We have a region we don't know. So we're going to put a variable there. And then we're going to solve for that variable by adding up the 4 regions and setting them equal to 32. So go ahead and solve for X and let me know what you get. So if we add 13, 5, and 8 together, we get 26. Subtracting 26 from both sides, we get x equals 6. So that means that there are 6 students that are taking physics, but not math, because that's what that half moon on the right hand stands for, right? It's the people that are in the physics, but they're not overlapping with math at all. So we're going to skip number 6 because it's confusing, honestly, the wording they use about being partially or entirely within the time zone. We're just not doing it. Let's move on to number 7. It's a better one. So number 7 says, in a survey of 1,000 investors, it was determined that 600 invest in stocks, 575 in bonds, and 300 in both stocks and bonds. Before you even get to the questions it's asking, just deal with what they give you in terms of the numbers, okay? So if we just focus on this first sentence, they give us a lot of information. It tells us that we have 1,000 total. And that those people are investing in stocks and bonds. And maybe some are not investing in stocks and bonds, they're investing in something else, right? So from here, we want to focus on the fact that if you can go to the overlap, that's always where we want to be first. So we can say that 300 are investing in both. So there's going to be 300 in that overlap. From there, we're going to work our way out. We know 600 are investing in stocks. That represents the entire stock circle. So we're going to do 600 minus 300, giving us 300 just stocks. Okay. The other number that we want to deal with is the fact that 575 are just in bonds. Again, are bonds. Again, that represents the entire circle of bonds. We've used 300 of that. So we're going to do 575 minus 300, giving us 275 there. The last region is this region out here. We don't know. Those are the people who are shoving the money in their mattress. They're not investing in stocks or bonds, or they're buying Bitcoin or, I don't know, emus. Who knows what they're putting their money in? They're investing it some other way, right? So we need to find that X. We know that the sum of the 4 regions, the stocks, the overlap, the bonds, and that outside has to all equal 1,000. So we're going to do 300 plus 300 plus 275 plus X equals 1,000. So 300 and 300 is 600, plus another 275 is 875. Subtracting 875 from both sides, we end up with X equals 125. So that means that there's 125 people doing something else with their money. Who knows? They're buying commemorative coins. I have no idea what else to invest in. I don't even invest in stocks and bonds. Okay, that's not true. I have a retirement account through work, but nonetheless, I don't know what they do with it. They just put money in it and they get to send me a statement. So once you've filled out your entire thing, right? The whole Venn diagram, we've got all 4 regions filled out. Now start looking at the questions. So the first question says, how many invested in only stocks? So only stocks, that represents the half circle that is just the stocks part. Okay, so only stocks is right here. So we've got 300 invested in only stocks. The next one says stocks or bonds. Stocks or bonds. This is the union of stocks and bonds. So remember, the union is, or taking the 2 circles, We're adding them up, whatever regions there are. So we're going to add those three spaces together. So we have 300 that are just the stocks, plus 300, which is in the overlap, plus those 275 that are just the bonds. So adding those up, we end up with 875 total were in stocks or bonds. It's either one, right? And then the last part was how many was neither stocks or bonds. And those are the people outside, right? That's this group right here. Those are the neithers. So they are going to be 125. So again, with these problems, always fill out your Venn diagram first before you try to answer any of the questions, okay? You can't even start thinking about the questions unless you have the whole thing laid out. So you got to do that part first. Okay. So we kind of touched on this, but let's look at this formula. It says, this is the union rule. Given two sets A and B, the number of elements in the union of A and B is equal to the sum of the elements in each set minus the number of elements in both sets. Meaning we're taking the two things, we add them up, and we subtract out where they overlap because we would have double counted them by adding the two individual ones. So it says find the value of A union B if A is 12, B is 14, and the intersect is 5. So the number of elements in A union B, again, is the number of elements in A plus the number of elements in B minus the number of elements in A intersect B. So plugging in what we know, there's 12 in A, 14 in B, and 5 in the intersect where they overlap. So what does that give us? Well, 12 and 14 is 26 minus 5 is 21. If we were to draw a Venn diagram to represent this, if I had A and B, again, we would start with the intersect. There's 5 items there. The number of stuff that's in 12, or in A, excuse me, is 12 for the whole circle. 12 minus 5 is giving us 7 left over here. For B, the whole circle was 14. 14 minus 5 gives us 9. So if I union these, that means I am adding all the regions up, which adding those regions up, 7 plus 5 plus 9. 7 and 5 makes 13. 13? 12, excuse me, 12, right? 7 plus 5 is 12. 12 plus 9 is 21. So you can see there's 2 ways we can get it if you want to draw the Venn diagram or if you just want to use the formula. Either one are going to get you to that answer. But you can see the reason we ended up subtracting the intersect is we had to even subtract it even to set up the Venn diagram. Because again, you're double counting because they overlap. So before we move forward, any questions on Venn diagrams? Okay. So, probability. First of all, in your notebook, on page something or other, page 173, there is a card and dice sheet. And this is just a visual representation that we're going to end up using later. We'll use it a little bit in 3C, and then we'll also use it in 3D. So that's just to show you what your sample space looks like with cards and what your sample space looks like with rolling 2 dice, okay? When it comes time to take the chapter 3 exam, this will be available to you. People in Libby will be happy to know that it's one-sided, so you will get all of it versus what I found out today that some of you got half, some of you got the other half, and that was not my intention. I sent a two-sided document. It just didn't get printed two-sided. So I'm very sorry. I will take that into consideration, knowing they told me who got what. So don't stress too much about that. If you've already taken your exam, I know about it. So probability, experiment. It's an activity with an observable result. So the repetitions of the experiment are referred to as trials. The sample space is a set of all possible outcomes for that experiment. The event is a subset of the sample space. So we're going to deal with tossing coins and rolling dice a whole bunch. So my experiment is me tossing a coin. The sample space are all my possible outcomes. An event would be I get heads or I get tails or something along those lines. The probability of an event occurring is the number of ways A can occur out of all the total possible outcomes, okay? The probability of an event is always between 0 and 1 inclusively. So we can't have something happen 110% of the time. Like, that's impossible. It either does or it doesn't happen, right? If it happens 100% of the time, it's a certain event. If it happens 0% of the time, it's an impossible event. Like, you can't go above 100% with your probabilities. The sum of all probabilities for possible outcomes for an event sums to 1. We'll talk about that more later. And then the probability of an event A not occurring is 1 minus the probability of A. And this is also referred to as the complement of A. And we talked about complements back when we had sets. So what is the sample space for a coin that is tossed twice? So I really like tree diagrams is what they call them. They're very nice and organized. So if we think about, I'm tossing a coin. Okay, this is going to represent my first toss. If I toss a coin, I can get heads or I can get tails, right? Those are my two possible outcomes. We're going to ignore the fact of the freak accident where we toss the coin and it lands on its edge on the table, right? It's either heads or tails. There's two options. After the first toss, we want to do the second toss. We can either get heads or tails, and we can get heads or tails. So when we think about the events moving through our tree diagram, I can get a head first and a head second, giving me the event of HH. I could get a head first and a tail second, giving me the event HT. With these coin tosses, we're going to assume that order matters. So we're going to say that getting a head tail is a different event than getting a tail head. I recognize that, right, they're the same thing, but again, we're looking at order mattering here. So if I move through my tree diagram, if I got a tail first and then a head second, that's a tail head. And then my last possible outcome is I get two tails. So the sample space written in proper set notation is head, 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 tail, tail, oops, head, and tail, tail. That is my possible sample space. Number 2 says, what is the probability that a coin toss twice will result in two tails? Well, if we look at our sample space, how many times does two tails occur? Well, two tails occurs once, right there, right? The probability of tail, tail is 1 out of the 4 possible outcomes we can have, right? Because there's 4 possible outcomes in our sample space, again, assuming order matters, right? Number 3 says, what is the probability that a coin tossed 3 times will have fewer than 2 tails? So in order to even answer number 3, we've got to look at what our sample space looks like. So if we draw another tree diagram, I'm gonna make this one little. So if I think about all my outcomes, I can have 3 heads in a row. I can have 2 heads and then a tail. I can get a head, then a tail, then a head. Where am I at? A head and then 2 tails. And those are the first 4 outcomes where I get a head first, right? I've exhausted all the possibilities. We now look at getting a tail first, which is going to be a tail and 2 heads. A tail, a head, and a tail. 2 tails and a head. And then the final outcome is 3 tails. So there's 8 possible outcomes when I flip this coin 3 times. So it says, what is the probability that I'll have fewer than 2 tails? So fewer than 2 tails means 0 tails or 1 tail, right? That's what fewer than 2 means. So if I look at my list, fewer than 2 tails, so I can have 0 or 1. So those are the possible places where I either have no tails or only 1 tail. So the probability that tail is less than 2 is equal to 4 possible outcomes out of the 8 total possible outcomes. And then, unfortunately, they make us reduce our fractions. So 4/8, I would divide my numerator by 4, my denominator by 4, and it reduces to 1/2. So before I move forward, I want to pause there. Questions about number 3, or 1 or 2? In math, having boys and girls and flipping a coin is the exact same thing, to be honest. The way that we treat it in math, we're getting it a 50-50% chance depending on male or female, just like heads or tails, right? In the world of math, we don't distinguish. So when we look at number 4, it says, what is the sample space for a couple that has 3 children? So honestly, the tree diagram for having children looks just like the tree diagram for flipping a coin, but instead of H and T, we'll use B and G. Okay. So I want you to go ahead and fill out your tree diagram. And write out your sample space. Again, you'll know you got them all if you have 8 possible outcomes in the end.
Did you want us to write that out to you in chat?
No, because it's a huge list. I just want everybody to draw it themselves instead of me sitting here droning on. Plus, I need to take a drink of water. So B's and G's instead of H's and T's. So we've got boy and we got girl. boy, girl, boy, girl, boy, girl, boy, girl, boy, girl, boy, girl. So we can have 3 boys. We can have 2 boys, then a girl. We can have a boy, then a girl, then a boy. We can have a boy and 2 girls. We can have a girl, then 2 boys. We can have a girl and a boy and a girl. We can have 2 girls and a boy. And then our last outcome is all girls, right? So if we write out the sample space, it's just copying those into our list. Right? So we should have 8. We do. You know, my girls get a little, my G's get a little slappy. So we need to use the sample space for the next page. So let me copy this. And go to the next page. And there's our sample space. So what is the probability that a couple with 3 children will have no boys? So it can be easier sometimes to find the complement of an event than it can be to find the event. So no boys, oops, no boys equals all girls. So the probability of no boys, there's only one way we can get all girls, right? 3 G's out of our total possible ways of having these children. Number 6 says, what is the probability that a couple with three children will have more than 1 girl? So I want you to try that one, more than 1 girl. The probability that G will be greater than 1. So make sure if we're counting more than 1 girl, we're dealing with 2 girls or 3 girls. So if I look at my list, I want more than 1 girl. So I want 2 girls. So that's 2 girls, that's 2 girls, that's 2 girls. And I want 3 girls. So there's 3 girls. So that means we have 4 out of a total 8, which reduces to 1/2 or 50% or 0.5. Your homework for the most part is going to ask for your answers as reduced fractions. Which for probability instructors, we get kind of frustrated with that because honestly, the fraction in its form of 4/8 is more descriptive. It's telling you that out of your 8 total outcomes, we can have 4 of what that meet the standard of what we want. But again, they're going to ask you to reduce them. So I don't want you to get it wrong, right? Just letting you know. All right, switching from kids to dice. So a die is rolled. What is the probability that the number rolled is even? So if we think about rolling a die, we've talked about the sample space a ton. We've got the numbers 1, 2, 3, 4, 5, or 6 that can come up, right? When I roll it and it falls. We want to know what is the probability of getting an even? Well, we have 1, 2, 3 even numbers. So the probability of even is going to be 3 out of total 6, or 1/2. So number 8 says a die is rolled. What is the probability of getting a 2 or a 3? So again, if we think of our sample space, we want a 2 or 3. That means we want those two numbers. So the probability of 2 or 3 is going to be our 2 possible outcomes, again, out of our 6 total outcomes, giving us 1/3 as our probability. Let's see if I can import that card and dice sheet so I can use it. Hold on one second. There we go. Okay. So looking at number 9, it says, given a deck of cards, what is the probability of drawing a red card? So if we go to our card and dice sheet, we can see our cards down at the bottom. And so you can see that it's divided up. We've got red cards and we've got black cards, right? So first of all, the total number for a deck of cards is 52 cards total. There are 13 in each suit, right? So there's 13 for each suit. So if we think about probability of getting a red, well, there's 26 cards that are red, a total of 52, which reduces to 1/2. And again, we can tell that 1/2 just by looking at it because 2 of the rows are red out of the 4 total rows. Okay, I want you to think about number 10 and send me your answer. Number 10 says, what is the probability of drawing a 10? So I'll give you that card and dice sheet in case you don't have it in front of you. What is the probability of getting a 10? So 10s, I've got 4 of them, right? Out of a total of 52 cards. So probability of a 10 is 4 out of 52, which we reduce to 1/13. Okay, number 11 says, what is the probability of a black 2? So again, card and dice sheet, send me your answer, black 2. So there's two black twos, right? Is a black two? Yep, there's two of them, right? Out of a total 52. So we get 2 out of 52, which reduces to 1 out of 26. So number 2 says, rolling 2 dice, what is the probability of getting a sum of 5? So if we look at our card and dice sheet, let's look at, so what the top part here is trying to show you is that the first die is going to be white and the second die is orange. And so how can these all land? So you can see you can roll a 1 and a 1, 1, 2, 1, 3, blah, blah, blah. So this lower stuff shows this is the order that we would roll those in. And then this is the sum that it corresponds to. So again, if I roll a 1, 1, those 2 dice sum to a 2. Okay. So we're looking for a sum of 5. So 5, the sum occurs right here, right? So how did I get that? Well, in order to get a 5, I could have rolled a 4 and a 1, a 3 and a 2, a 2 and a 3, or a 1 and a 4, right? So the probability that the sum equals 5 is 4 possible outcomes out of 36 total ways. And again, that's assuming that our order matters with those dice, right? Hence why we have different colors for them. So we have 36. How do I know there's 36? Because I have 6 rows, 6 columns, giving me 36 total possible outcomes. So if we look at our thing, again, the probability that the sum equals 5 is 4 out of 36, which reduces to 1/9. Number 13 says rolling 2 dice. What is the probability of getting a sum less than 7? So if we think about less than 7, again, less than 7 are going to be these possible outcomes here. So we just have to add those up, right? So you tell me what you think the probability of getting a sum less than 7 is. So if we count these up, we've got 1, 2, 3, 4, 5 in the first row, plus 4 in the second row. So we're now at 9, plus another 3, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 total. So the probability that the sum is less than 7 is 15 out of 36, which we can reduce to 5 twelfths. All right, number 14 again has the idea of these complement of events. So it says if the probability of rainy weather is 0.3, what is the probability of non-rainy weather? So basically it's raining or it's not. Don't give me this, well, it's misting outside, it's not really rain. It's still moisture falling from the sky, but we're not calling it rain, right? It's either it's raining or it's not. So the probability of non-rain is going to be 1 minus the probability of rain. Here, let me write this out so we understand where this came from. Probability of rain. So plugging in our values, 1 minus 0.3 is going to give us 0.7. So we have 30% chance of rain, 70% chance of non-rain, right? They're complementary events. They're opposites of each other. And then number 15 is our last one. It says, suppose a bag contains 15 white marbles, 10 purple, 7 red, 3 yellow. We throw them all in there together. I want you to tell me, what is the probability of purple? I reach in, I pull a marble out. What is the probability I get a purple one? So we have 10 purple out of a total of, well, 15 plus 10 is 25, plus 7 plus another 3 gives us 35, which we then reduce to 2 sevens. So the probability of purple is 2 sevens. Whew. We did all the stuff. I'm not going to go into 3D. We're going to leave that till next week. There's no reason for us to get all that ahead. You took a test today, or you will be taking a test today. You got stuff to do. You're tired. So I'm going to stop us a little bit early. Again, remember, because you took a test today, we do not have lecture tomorrow. So A, you're getting out early, and B, you get off tomorrow. So ta-da, you're welcome. No, I'm kidding. We've already put the work in. All right, everyone. So just remember that to do your test, do your homework. I will see you Monday. Email me if you have questions, okay? That's all I got.
I guess I have one little question, and it's probably super obvious. I'm just missing it. On the dice, rolling 2 dice, the probability of getting a sum of 5. For some reason, my initial reaction was, if you get a 4 and a 1, that's 5, and a 2 and a 3, that's 5. But I guess being more specific, looking at the sheets, it matters like if a 4 is rolled first, then a 1, not like combined. Because I was trying to think of like 2 chances. Well,
yeah, and that's why the dice has colors, because we're trying to indicate to you that order matters. So if the probability, if we said, what is the probability we get a sum of 5, we would have reduced our overall sample size by removing the redundancies. And so if we do that, right, so if we look at that, I mean, that's a good, so we can see that what are our possible sums that we can get. So if we go through and we take out our redundancies, right? Let's see, 1, 2, 2, 2, 3, 2, because we get the 2, 3, 4, 2, 5, 2, 6, 2. Oh my goodness, 4, 3, 5. Nope, no, I need the double because, right? So that's showing us that we've got this sample space here. Oh, I need that 5, 5, don't I? And I need the 6, 6. Okay. So we've got 1, 2, 3.
We might need the screen share possibly. I'm not.
Oh.
Yeah, coming? Sorry. I wasn't sure if you're gonna like pull something up afterwards.
Oh, yeah, I'm sitting here drawing, pretending I know what's going on. Come on.
Yeah, definitely not trying to add more confusion to this or anything. I just, for some
No.
reason.
So we're looking at 5. So we're gonna have 2, 3. So yeah, 21. So if we were to remove the possibility of redundancy, then we get a different probability, right?
Mm-hmm.
But because we can have redundancy, what it does is it gives us outcomes that are more likely to happen because there's more combinations for making them.
Okay.
And so if you want, I mean, really, that's like all gambling in is probability, right?
Mm-hmm.
And so if you were to be playing a game and I said, I'll bet you, like, you wanted to place a wager on what the sum was that you would get, you would go for betting on a sum of 7 because that is the highest probability of coming out. Well, the house would then have that be the lowest payout, where the highest payouts would occur on 2 and 12 because those are the least likely to happen, but would cause people to bet on them because they're like, oh, I can make a ton of money on it. And the house is like, please, you're going to lose a ton of money by betting on this. So we have to consider order mattering here because technically speaking, when one dice is white and one dice is orange, it's a different outcome because they're going in different order.
And kind of what I brought up, would that ever be like worded as a question maybe that we might run into or
we
not?
never deal with that. Yeah,
Okay,
we don't deal with that.
Okay, well, that's good. Yeah.
Yeah, no, I don't ever ask like I don't think we have it in this class. If you're going on to 115, there's a question about drawing slips of paper and drawing 2 slips of paper and not replacing them. And the only thing that does to the sample size is it removes the redundancy numbers. But other than that, it's not like we're not fully removing the redundancy.
Right on.
But in this class, we're not going to deal with that.
No, yeah, that's good. Yeah, just that. I mean, yeah, it's nice to know that way. My mind won't drift that way in future homework or something. So
there you go.
All right. Well, good to go.
All right. Well, have a good one, Luke. I'll talk to you later.
Catch you later.
Bye.
See ya.
Wesley or Taylor, do you guys have any questions?
I have a question about the Earth area project.
Sure.
On the top right, we're supposed to convert kilometers to miles to square kilometers to square miles, and
yes.
I'm not sure how to do that.
So think about a square kilometer. I'm giving you your conversion factor, and squaring means that we're multiplying it by itself. So you would be taking that unit and the unit that I give you in the straight unit conversion, and you'd be squaring that unit to create the squared unit conversion.
Oh, so you just multiply the kilometers you get to square kilometers by multiplying it by itself?
By itself, yeah, exactly. And I think I go over that in the video. So I would check out the video that's in Eagle Online for that project.
Okay.
Okay.
And just the first part of this lesson was recorded, obviously. I'm sorry.
Yes, the whole thing was recorded. So once we end and it processes, it'll probably take a couple of hours for it to like finish processing and like, cause I have to upload it to YouTube and all of that. But then it'll be there and you can go back and watch it.
Perfect. Yeah. I was just running a little late today, but okay.
No
Sounds
worries.
good. Thank you.
I get it.
All right, have a good one.
You too, Taylor.